Thanks, Richard. I've worked in the water industry for most of my career, and I've been at NEL for the last couple of years. I chair ISO TC30 SC7, which is responsible for ISO 4064, and I'm also co-convener of the OIML committee responsible for R49, and these are the standards relating to water meters. So, this webinar is on the EMPIR-funded MetroWaMet project to investigate how accurate domestic water meters are in the real world, how they perform under real world conditions. This is an update on the webinar that was presented last year in June 2020. The full results of this project will be presented in a 2-day workshop to be held in Berlin in September, and further details on that workshop will be presented at the end of this webinar. So, a quick introduction to begin with. As I'm sure most of you know, domestic water meters have to conform to prescribed levels of accuracy. They have to be within a maximum permissible error. And there are international standards and regulations which make sure that this is the case, and meters have to be tested and fall within the guidelines. The test procedures are carried out over the whole of the meter's flow range, but they're carried out under constant flow rates, which is very different from real life. You know, with washing machines, dishwashers, showers, hand washing, etc., taps and valves are turned on and off, so the flows are far from constant and can change rapidly. Does this pattern affect the meter accuracy? Also, the test procedures are carried out with water from the local public potable water supply, but the water quality varies around Europe, and how does this affect performance? Also, smart meters becoming more widely common in water networks. How well can they detect leakage, and what criteria do they need to be able to meet to detect background leakage? And can we estimate in advance how a meter will behave under different conditions? To answer these questions, they set up an EMPIR-funded project, MetroWaMet, Metrology for Real-World Domestic Water Metering. And the project aims at establishing a metrological infrastructure to characterize domestic water meter performance at close to real-world conditions and not at laboratory conditions as is done presently. The project duration is from June 2018 to September this year. It was due to finish in May, but due to COVID, it's been extended by a few months. And there's details of the websites, the EMPIR and MetroWaMet websites here if you want to look at those in more detail. The project also includes an advisory board with representatives from various stakeholders, manufacturers and users. The participants of this project come from all around Europe. There's NEL from where I work up in Scotland, PTB and DVGW in Germany, CETIAT in France, BV PTP in Austria, ENISA in Italy, TÜBİTAK in Turkey, CMI in the Czech Republic, DTI in Force in Denmark, VTT in Finland, and RISE in Sweden. The project was split into a number of work packages, which I will describe in the following sections. And work package 1 looked at whether dynamically changing flows affect meter accuracy. Experimental facilities were set up to test this at national metrology institutes and designated institutes in several countries. A pilot study of the EuroMet interlaboratory comparison was undertaken to validate the metrological comparability of the dynamic test facilities. And this was to ensure that the dynamic flow profile capability of all the dynamic test rigs was the same. And to test this, a transfer standard, also called a validation module, was circulated around all the laboratories and recorded how well the facilities matched the dynamic test profiles. And the picture on the right shows what it was. It's basically a case containing a Coriolis mass flow meter and pressure and temperature sensors, plus a dedicated logging system. This slide gives a few more details of the system. And basically, it was all in a shipping-friendly package with dedicated software that was sent around the various labs to measure the performance of the test rigs. The pilot study was performed with 3 flow profiles with different volumes of approximately 50, 80, and 100 litres, simulating dynamic flow load changes and flow rate range up to 1600 litres an hour, which is 1.6 meters cubed an hour, and flow durations down to 10 seconds. The selected flow profiles were determined on the basis of previous studies of consumption data from various apartments and apartment buildings in a number of EU countries. These data were evaluated in relation to flow rates, their durations, and speed of flow changes. The flow profiles were chosen with respect to the laboratory's capabilities, and so that the flow profiles are statistically representative of the actual water consumption in households. And each flow profile represents a different situation for which the participating laboratory had to demonstrate its capacity to handle different flow profiles. So for profile number 1 on the left, it starts with a medium flow rate and ends with a medium flow rate. Profile 2 in the center starts high and ends medium. And flow profile 3 on the right starts with a 0 flow rate and ends with a medium flow rate. So in order to match these profiles, they had to fulfill a number of requirements. And that meant fast changing flow rates overall from high to low, almost instantaneous in some cases, but slightly slower for the higher flow rate changes. And with a high resolution in measuring the flows. This unprecedented intercomparison gives the first overview of the calibration and measurement capabilities of 8 European national metrology institutes and designated institutes regarding dynamic flow measurements. In the table, there's an overview of the participating laboratories, the type of facility, the calibration procedure, and the flow change technology. All laboratories used a dynamic method of measurement, and all were completely independent of each other. All the participants had different primary standards technologies for the generation and measurement of dynamic profiles. The primary methods included gravimetric weighing, volumetric using a piston prover, and one partner used a reference flow meter. Dynamic flow generators were used to create rapid changes in flow, and these included fast valves, critical nozzles, digital valves, and fast piston changes. A test protocol was prepared, which was followed by all the laboratories, and this shows the log sheet to be completed for each test, which was repeated at least 3 times. The degrees of equivalence observed in this intercomparison show that the test facilities for dynamic liquid flow calibrations of the participating laboratories are in very good agreement. Despite the fact that 3 different technologies were used to create the load changes, the relative errors for the 3 profiles agree within a range of -0.1% to +0.2%. And the participating laboratories state the expanded measurement uncertainties of their test facilities as being between 0.1 and 0.4%. With a view on future broader applications of this kind of calibration, an in-depth analysis of the profile realization using the individually measured data sets will be carried out by the end of the project. The dynamic measurements are being compared with the results of steady state flow tests for different meters. And this graph shows an example of how the results might be presented. Further evaluations of the measurements are currently being carried out and will be presented at the workshop in September. Work package 2 looked at the effect of water quality on long-term meter performance. It's known that water quality can significantly affect the measurement performance of domestic water meters, and there are a number of studies carried out in Central Europe over the last 10 years, but they didn't yield any clear correlations between meter performance and age, total recorded volume, or water quality. So therefore, it was considered extremely helpful if laboratory tests could be developed to back up the field investigations in order to be able to anticipate eventual problems. So what conditions is a domestic water meter exposed to? What's the total throughput, typical loads? What's the parameter ranges of tap water? The determination of the boundary conditions for the tests were based on surveys on consumption characteristics, and that's a paper in this project, and surveys on tap water quality that have been carried out recently. And again, there's another paper available. So the boundary conditions were found to be that a total throughput of 189 meters cubed in 6 years for a meter with a Q3 nominal size of 2.5 meters cubed per hour, with typical flow rates being 0.75, 0.8 meters cubed per hour. And for these tests, this representative load profile on the right was repeated over 10 days until 189 meters cubed was passed. As a comparison, the steady state test from OIML-R49 is 100 hours at Q4, which is 1.25 times Q3. Basic tests were set up to evaluate separately the effect of hardness, pH, and particles. And 3 different values of these parameters were tested based on the European Water Survey. Note that the typical values were used for hardness and pH, not extreme values, and that resulted in the values on the slide. Information on typical particle loads was difficult to find, so sizes and concentrations were selected that could potentially be experienced in networks. Then a number of cooking recipes were set up to make up water of consistent quality and to make sure that the quality was identical across all laboratories so that the results be comparable and repeatable. The tests were carried out using that profile shown in the previous slides. Details of these test rigs were presented in the previous webinar, so I'm not going to go through them again here. As said before, the experiment was continued until the total throughput of 189 meters cubed was reached. The pH and hardness of the test water were monitored at regular intervals, at a minimum of every 2 to 3 days, using either handheld devices or laboratory measurements. In total, 187 water meters from 9 different companies were investigated, and manufacturers supplied at least 3 meters of each type. And an overlap of meter types, experiments, and test regimes was ensured. At a later stage during the test, additional experiments were undertaken on selected meters, which included a higher hardness of 6 millimoles per litre, a doubling of the experiment duration, a combination of hardness and particles, and also the OIML-R49 stress test of 100 hours at 3.15 meters cubed per hour with local tap water for comparison. So here's some results of tests on meters in mint condition. These are baseline tests carried out so that they could, for comparison with later experimental results. So these were the baseline tests. And it also gave an insight into the differences in measurement performance that already occur with new water meters. These base measurements were evaluated with regard to the variability in the measurement deviation depending on the meter type. And then these were used later as a reference to determine changes in the measurement deviations depending on the water quality. The graphs show the mean and standard deviations of each point. Mechanical meter results are shown on the left and electronic meter results on the right. The graph axes are the same. And a number of things stand out. The measurement deviations for a single meter type and company can vary considerably, as can be seen from the bars showing the standard deviations. In general, water meters based on electronic measuring principles show smaller measurement deviations, but there are obvious exceptions, e.g. piston-based meters can have similar measurement deviations of a similar order of magnitude as ultrasonic or magnetic inductive meters. An ultrasonic meter can have larger measurement deviations than mechanical water meters. And that's for, can we see on the graph, it's for company B with a meter of R160. Another point to note is that the largest measurement deviations do not necessarily occur at the smallest flows. And a water meter type from one manufacturer with different R ratios does not necessarily have the same measurement deviations at the same flow rates as can be seen for another manufacturer. The main conclusion of the investigations is that no generally valid statements can be made about the measurement performance of a particular type of water meter, but at least the combination of meter type plus manufacturer should be considered. From the outset, there is a range of variation in the measurement deviations of 1% or more per flow point, without taking into account the standard deviations of the individual measurement points or the measurement uncertainty inherent in the test rig, which must be taken into account when assessing whether a certain water quality parameter affects the meter performance. This shows the difference between the measurement deviations obtained after testing compared with the individual meter in mint condition. The bars indicate standard deviations before. The yellow bars are the hardness experiments, the green bars are the pH experiments, and the grey-black bars are the particle experiments. And these are shown divided up into the different meter types. Please note that the scales on the y-axis are slightly different, not the same for all the graphs. As already observed for the measurements on new meters, the results for the influence of the water quality on the measurement performance of the water meters shows no clear patterns. A lower water quality due to hardness, pH value, or particle load can cause measurement deviations in water meter performances. In many cases, the changes in the measurement deviations are in the range of up to 1%, often well below. There is no consistent change in the measurement deviations compared to the new meter measurements, i.e. no systematically increasing or decreasing deviations. The largest effects do not necessarily occur at the lowest flow rates or the poorer water quality. Several examples were found where the maximum effects occurred at pH 7.7 and flow rates between 0.8 and 1.8 meters cubed per hour. Compared to the OIML R49 stress test, the water quality related changes in the measurement deviations are at least of a similar order of magnitude, often significantly larger, up to a factor of 10. There is an impression that water meters with an electronic measuring principle tend to have less of an effect related to water quality. However, this has not yet been reliably proven on the basis of the meters considered so far. In the examples where single-jet and multi-jet water meters were installed vertically and horizontally, the vertically installed meter had the greater effects. The combination of a high hardness value and particles did not lead to significantly different measurement deviations than those of the individual effects. The extension of the experiment time by another 2 weeks at a hardness value of 6 millimoles per litre showed a slightly greater effect in comparison. However, a comparable experiment with a water hardness of 6 millimoles per litre plus particles did not lead to an increase in the measurement deviation after the extra 2 weeks. So to conclude, the test regimes were feasible. The type of test regime doesn't seem to play a role. The test waters were stable during the tests. There were indications that poorer water quality leads to stronger effects than conventional stress testing. The results show no clear trends and strongly depend on the combination of water type and manufacturer and possibly the batch. All these results were made available via a user interface accessible at the project website towards the end of the project. Generally, the measurement performance of the meters was within the maximum permissible error, but not all, and not even all meters in mint condition complied with the MPE. The objective of Work Package 3 was to assess meter performance in detecting leaks and low flows. Different types of water meters perform differently at low flows, and that depends on their construction, their measuring principle, which affects both the starting flow and their dynamic performance. And the meter types have different cutoff values for low flow. For mechanical meters with rotating wheels, they need some flow before the wheel begins to turn, whereas an ultrasonic meter does not have a mechanical part and a force to overcome before they can start measuring. The purpose of the leak detection part of the project was to look at different types of domestic flow meters performance at low flow and for different dynamic profiles, and investigate different flow patterns, flow profiles together with leakages, develop algorithms to detect leakage, and an electronic solution to detect leakage as well. Laboratory facilities were set up to simulate different leakage experiments in controlled settings, and leakages were generated by a defined opening of a needle valve between values of 0.1 and 3 litres per hour. As can be seen here, there are two leakage types, which are a constant drip or a gradually increasing leakage rate. And the volume of leakage was measured using a gravimetric method, i.e. with a weigh scale. Two sets of experiments were performed by testing flow meters both with and without leakage, and by superimposing leakage on a dynamic profile. For this, a Coriolis meter was used as reference for the comparison of water meters of different types. Derivation of leakage criteria is currently being analysed. And the example graph of a leakage of 3 litres per hour was selected to be presented here because it's easiest to see on a plot. For a leakage rate of 0.1 litres an hour, it wasn't possible to detect it visually from the data set. It would be necessary to analyse the data, e.g. by looking at differences between data sets. Three dynamic profiles for low flow were generated using the same methodology as in Work Package 1. And for these tests, the maximum flow was set to 30 litres per hour. The three profiles were used for an intercomparison between two labs using a transfer standard for comparison. And the transfer standard was compared against each lab's primary gravimetric reference. The table shows the results for the intercomparison between the two labs. An E value is calculated, which shows how well the lab's results compare, with a value of less than 1 being the criterion for good agreement. As you can see, all the profiles and repetitions met this criterion and so confirmed good agreement between the labs. After validation of the setup, the three different types of water meters were tested under the dynamic load of low flow rates: ultrasonic, multi-jet, and piston, and they were all of the same flow rating of 2.5 meters cubed per hour. And then each profile was repeated, it says 150 times, giving a total reference volume for the two profiles. Profile 1 with 207 litres and Profile 2 of 173 litres. Unfortunately, Profile 3 had to be excluded due to the hardware problems of the reference system. And these show the results for the different meters, with the meter ID along the bottom and the percentage error in the y-axis. The ultrasonic meters are outlined in the green dotted line, and as you can see, they're very close to zero error, as are the piston meters in general. For the multi-jet meters, they have the largest low flow cutoff value, i.e. the minimum flow at which the meters start to record, and therefore they under-register significantly at the low flows tested, as is shown on the graph. So the first step in checking out the leakage was to generate some typical consumption profiles. These profiles are based on observations at a household level from a project in Germany, where consumption was measured at 1 second intervals in small and large buildings. And the 4 profiles shown on the left are randomized sets of the following consumption types: toilet and hand washing, shower, bath, dishwasher, washing machine, and a partly opened valve, e.g. using the tap for anything else. These were then used to generate an annual profile, so to generate 365 daily patterns. And each daily pattern is created by a randomly sliced set of the 4 consumption profiles on the left. For example, 30% of profile 1, 25% profile 2, 10% profile 3, and 35% profile 4. To make it more realistic, some peak water demands, spikes, were added to the data. And finally, towards the end of the year, a slowly increasing leakage flow was added. And this could be a small pipe burst that gets larger over the time. And then in the end, you get a nearly realistic yearly consumption profile of a household, seen here on the right, by overplotting all 365 days. The algorithm used to detect leakage comes from the water loss analysis in large-scale water distribution networks. In these networks, you estimate the overall water loss by carrying out a water balance on the water meters in the network and subtracting other legitimate metered and unmetered use to give a value for unaccounted for water, i.e. leakage. This multivariate approach was downscaled to a univariate approach, i.e. one household, one water meter. And it basically consists of 2 major approaches. The first approach is the assessment of recurring states in the data. So pattern recognition techniques, non-negative matrix factorization, were used to reduce the variability of data to a few recurring patterns. And the second approach was to try to forecast each day by its pattern with linear or nonlinear regression models. The deviations between forecasted and real data should therefore be considered a loss, e.g. leakage. So the methodology is to look at an anomaly during the night, i.e. a spike, an anomaly during the day, another spike superimposed on the profile, a baseline anomaly, so leakage, so where the whole profile is lifted by the leakage amount, and an anomaly of the profile where it no longer matches the normal expected domestic consumption profile. And finally, the algorithm is capable of classifying and quantifying different occurrences of water loss. For our study, it's the upper right anomaly, the leakage, which is the interesting one. And these are the results of the algorithm. The pattern recognition algorithm detected 5 patterns from our data, which are basically the 4 water use patterns plus the leakage pattern. And the detected and measured profiles match perfectly. Pattern number 5, down at the bottom left-hand corner, is the is our leakage. The outcome of the algorithm, a time series separated out into its identified components. Yeah, the first line and baseline correction at the top looks at stands for the increasing leakage. The second red line in the center and the third purple line at the bottom correspond to the introduced peak demands occurring during the day and night, respectively. And, well, actually, night and day, respectively. The overall quantification of the losses or leakage is shown in the graph on the right-hand side. Some hardware was also developed for leak detection. The platform is based on a camera and image-based analysis of small rotations of the numbers or pointer on the water meter mechanical readout. And this is analyzed using a Raspberry Pi. The hardware module fits on top of the meter, and the camera can be positioned to see the water meter register. And it includes an LED-based lighting system to illuminate the display for the camera. And this shows different views of the same hardware, including the red arrow shows where the camera can be slid backwards and forwards, so it's lined up with the display. The image detection is based on correlation analysis, where two adjacent images are compared. The distance of movement of the dial can be evaluated, thereby enabling the hardware platform to detect slow movement of the dial on the water meter register. And two examples of the images are shown for a multi-jet meter. In each row, the picture on the left is image 0, the first image acquired. The picture on the right is image n, the last image acquired, and in the center is image n-1, the image just immediately preceding the last image. This slide shows the different correlation results, both for static and dynamic load profiles. For the algorithm output in the center, the red line shows the correlation, the blue line is a moving average, and the green line is the threshold value. At the top right, the static profiles show the output of a multi-jet meter in red and a volumetric meter in blue for different flows. The dynamic profiles show graphs of flow, the two correlations, and their respective moving windows. The final section covers details of the workshop mentioned earlier and the publications produced during the project. There's going to be a 2-day MetroWaMet workshop on the 15th and 16th of September at PTB in Germany. This is planned to be face-to-face. Obviously, we can't promise anything with the current COVID situation, because this will give much more scope for discussing results with the researchers and so on. Whether this will be possible or not will be decided closer to the time. Everyone is welcome to attend, and the detailed results of the project will be available by then and will be presented. To register for this event, please, you can go to the project website, select information and communication from the tabs, and then news and events from the drop-down list. You can also, if it's possible, from the slides which will be sent, you can also click that direct link, which will take you straight to the registration page. There are also some new recommendations which are now available to download from the website, and that's dealing with how to acquire consumption profiles, household consumption profiles, including guidelines for equipment, timescales, and sampling rates. there are other documents that are currently or will soon be available for download on the website. There are 3 open access publications which have already been submitted and published, and those are detailed here, together with their links. There are more papers in preparation, and they're going to be submitted in the next few weeks and should be available by the end of the project, I hope, and certainly will still be available on the project website. Finally, I'd like to acknowledge the funding we've received for this project from MetroWaMet through the EMPIR initiative. For further details of the project, please visit the MetroWaMet website, or just search for MetroWaMet if you can't click the link. And I think it's time to hand back to Richard for the Q&A.
Thank you very much, Sarah. So yeah, let's run through some of the questions where we received a few. So the first question I've got is there a significant difference in the results between testing water meters based on a static or a dynamic regime?
This is currently being looked at. This is being investigated for a small set of water meters. It wasn't included in the initial project definition. The report on the investigation should become available in a few weeks' time. Nothing much is going to get published in July and August, as that's the summer holiday season in Europe, but it should be available in September once everyone is back.
Very much. Next question, when will the results of the pilot study become available?
The first draft is being circulated for comments and is being revised and finalised at the moment. There's also a metrologia paper which is being written in parallel with the draft report. So more results should be publicly available in the autumn, and of course all papers will be open access. This is required by EMPIR.
Okay, perfect, thank you. And I think the last question we're going to have time for today, any further questions we can answer offline, is are the mixing recipes for the test waters available to any interested party?
Oh yes, they're currently available by request from the project participants. There are 2 publications which are currently being prepared, and these will also include the recipes, as well as full details of all the tests and the infrastructure. And once they're accepted for publication, they'll become available.
Okay, perfect, thank you. So that kind of concludes us today. So I'd just like to say thanks again to everybody for joining us. As we mentioned earlier, we will be sending you an email with a link to a copy of the presentation and the recording. And please feel free to visit our website at www.tuvsud.com/UK for more information. On behalf of myself and our presenter, Sarah, I would like to thank you for taking the time to join us today, and enjoy the rest of your day. Thank you very much.